So we'll be looking at conditional probabilities today, and we will be extending some of the ideas from the previous lecture. Just for the sake of those who have not gone over the recording of the previous session, I'm just going to quickly go over some of the results. I'll just summarize some of the results from our roulette wheel case study. So remember that we looked at some probabilities, probability of obtaining a black, of getting a black, that is your ball spinning in a black. Is this probability of getting a red? Is this probability of getting a green? Is this? So this black is 18 out of 38, red is 18 out of 38, and green is 2 out of 38. So this is the smallest. Just a Okay, so I just hope you can remember this. The total sum of all events in a sample space is 1. So the probability of a particular event, so the probability of every other thing outside that event gives you 1. So we also did some computations like combining more than one event. I think I've been talking from the wrong mic. Okay. I hope you can hear me, guys. Hello.
We can hear you.
Yes, I can hear you.
Yes, I can hear you.
Okay. All right. So we also did some probabilities like the event B or R, which of course you have to add all the outcomes or the events together, and then you check the probability. So it's just simply the probability of B plus probability of R. But this only works when you have mutually exclusive events, that is, events that do not cross or they do not have common outcomes. So a black and a red are entirely two different events. They will never, you can never have an outcome that is both black or red. Okay, but you can also have some inclusive events or intersecting events, such as the probability of, the event black or even. So when you're checking the probability of a black or even, it's not enough to just add these two, because if you add the two, you're going to be getting repeated elements inside, duplicate elements. So the goal for you is to remove the duplicate elements, which is why we remove the intersection of B and E. So the intersection of B and E is that area in the set where you have common elements between the two. You have to remove that out to just leave the those base elements. So let's say you have common elements like 2, 6, 8. You're going to be having them doubly twice. You would have 2 twice, you'd have 6 twice, you'd have 8 twice. So, but if you remove this intersection, you remove 2, 6, 8, leaving just 2, 6, 8. So you're not going to be having any duplicates. I hope that makes sense. So in that last session, in the recording, of course I continued the recording that night. So you'll be seeing some Venn diagrams that I added to make all these illustrations. So this is like the probability of, the events black and even. You can see that they overlap. So this middle, we have 18 outcomes for black, 18 outcomes for even, but we have 10 outcomes for black and even. All right. So Normally, if you just add black and even, that should be 18 plus 18, which is 36. All right, but it has already included 10 additional elements. So separately, that is in this case, it's 18 plus 18, which is 36. All right, but in this particular case now, it is you see that some elements are common, so you cannot do 18 plus 18, 36. You have to take away the extra 10 that will be duplicated here, because this black contains that extra 10 of even, what's it called, even outcomes. The even also contains 10 of black outcomes. So you have 10 black even and 10 black even. You have to remove one of them. Okay, so that is the intersection you're removing when you want to compute the probability of getting um, black or even when you have intersecting events. So the first case where there are no what's it called, common outcomes, is mutually exclusive. All right, I explain what mutually exclusive means. Exclusive because they do not share anything in common. They are not inclusive. There's nothing that includes or that causes any inclusion between the two. So this one is excluded from this. They share nothing in common. Mutually, because the one thing that these two share in common is the fact that they share nothing in common. So mutually exclusive. They have that one thing in common. They share nothing in common. Then in this case of intersecting events, these are mutually inclusive, which means, look here, there's something different about us, different about us compared to the last situation. In this particular case now, we share an interesting thing in common, and that's the fact that we actually share outcomes in common. So we are mutually, or we are mutual, or there's something mutual about us. That is, we share something in common, and that is the fact that we are inclusive. We share outcomes in common. I hope that makes sense. So then I looked at exhaustive events, which means events where you're looking at um, all the possible outcomes in the entire sample space actually rests within these two events. So the number of elements in A union B is the number of elements in the entire sample space. All right. So for example, exhaustive events would be something like, in the case of our roulette wheel, uh, um, the black, even, and green, if you take their union, they become exhaustive events. So the number of elements in black, green, and red is the entire number of elements in the sample space. So in order for any event in the roulette wheel to exhaust all the possibilities, we need to take the three events together. Two events alone in that roulette wheel cannot make up the entire number of possible outcomes in the sample space. But generally, this is what you have. If you have A and B, two events A and B, if the number of elements is simply the number of elements in the sample space, then those two events are exhaustive events. Because if you look outside A and B, you will not find any other outcome within that sample space. All the outcomes you have in the sample space rests in the union of A and B. So we computed some numbers. We looked at the probability of B intersects R, that is black intersect red. You already know that black and red are mutually exclusive, which means they have nothing in common. Therefore, the intersection of black and red is 0. So whenever you see intersection, that is and. Probability of getting both B and R, okay, means intersection. And in the case of mutually exclusive events, it's 0. Let me change this to this. All right. Now, when you look at probability of B intersect E, there are elements in common, that is black and even. Okay, the probability of the occurrence of black and even is simply divide 10, because there were 10 outcomes that are both black and even. So you divide 10 by 38, you get this. And probability of B union R means probability of B or R. So when you do union, that's all. So you're simply adding. Okay, so union will require you to add. So for mutually exclusive events, you just simply add, you get the sum. But for intersecting events like B union E, you're not going to just add B plus E. You would have to remove the extra intersection B intersect E. So it's simply uh, 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 the event E is also 18 over 38, just like B is 18 over 38. So if you add the two together, you should be getting 0.9472. But now you need to subtract this. So if you subtract this intersection from the union, not union, but from the total sum of B separately and E separately, okay, which means from this value 0.9472, you should be getting 0.684. So these are like the things we looked at here. But now, let us look at something more interesting than just these simple bets. Okay, we're having bets based on, or we're placing bets, based on prior information that, prior information about certain events without knowledge of any other kind of events. For example, if you are trying to bet, okay, you ask to bet, so you say, okay, I bet on black or even. The what's the name of this person that would do the spinning? Is it the croupier? The person, let's say he. So the croupier would spin. Okay, then watch whether the ball lands into black or even. So you already calculated the odds. Okay, the odds look like they're in your favor. Black or even is 0.684. It's not as strong as the odds of black or red because that one is stronger. They are not mutually exclusive. Right, but this one is still nice. So you look at it, 0.68, that's 68%. So the odds look like they're in your favor. So you place that bet. The person spins the ball, and then we watch the outcome. Okay, the outcome, if you're lucky, you could get that, you could win that bet. But what if it falls somewhere else? Okay, so the challenge with this kind of bet is that you don't have information about other events. So if you're trying to place a bet on B or E, you already know what the odds are, the information is available, but the probability you're calculating is irrespective of any other type of event. If you're trying to place a bet B or E, you are placing this bet without knowledge of the outcome B or R, without knowledge of the outcome B or even just B itself or E itself. Okay, why? Because those outcomes have not happened. So you can't make or place a bet based on those informations. You don't know what those things are. But what if there's a way you could know what a particular outcome is, and then you are asked to place a bet, okay, on any event of your choice based on that extra information that has been given to you now. You can see with this, we're already getting into the second interpretation of probability that I explained in the other session. Where I was telling you guys about the first case is frequencies. We just do some counting and divide and get a probability. But in the Bayesian interpretation, we're now looking at computing probabilities based on information available to us. So our probability is based on our degree of belief, in the possibilities of an outcome. And so it is based on how much information we know about that outcome. I use the earthquake example to say that if you ask to calculate the probability of an earthquake happening in Nigeria, you would very likely be computing a very small probability. But let's say suddenly an earthquake happens in a nearby country, we will need to revisit our knowledge about the topography in West Africa. We will need to check some other things. We even need to test topography in Nigeria and probably check if there are there's some metrics they normally use to predict earthquakes. We'll start checking all those metrics, and with that, we can then update our degree of belief based on the additional information. So this is where we're entering into now. Okay, so previous law that we have looked at here is just calculating events without extra knowledge of any other kind of event. But now we want to look at an alternative scenario where, not alternative really, but an additional scenario where we are now, before trying to compute this probability, we are now getting information about some other event. So we want to calculate a probability given that we know that a certain outcome has happened. Not just computing the probability on its own, that is trying to determine what the outcome will be without considering any other outcome. But now we want to now go further to compute what the outcome of a certain event will be, given that we already know that another event has occurred. So with the knowledge of another event occurring, is that knowledge going to, going to affect our probability? By updating that knowledge, is our degree of belief going to change? Is it going to improve? Is it going to decrease? So that takes us to the subject of conditional probabilities. All right, so I've given some background about that. So let's dive into what we have here. So we're going to revisit the roulette wheel. Okay, I've already explained this first bullet points. You're trying to assign probabilities. That's in the previous case. We're trying to assign probabilities to events without accessing knowledge of another event. So let's say you want to compute the probability of B or E. You're just going to compute that to know what the outcome, or to estimate what the outcome might likely be, to estimate the likelihood. All right. So you're not trying to compute it with knowledge of another event, because you don't have knowledge of another event. For you to have knowledge of another event, that event must have occurred, and you must get information about the event. So it is this, based on this information, we can then use it to update the probability we are assigning to the event we are trying to predict. I don't know if I'm making sense. I hope you're with me. Okay, various shares with me. Anyone else? So that I just know I'm not alone. All right, moving on. Okay, so moving on. Let's now try to, move from this scenario. Okay, this scenario, and uh, um, okay, before we go to the next scenario, let's look at this unlucky spin. So you place the bet B or E. The croupier spin the ball, and unfortunately the ball landed on 5. Where's 5? If you look at 5 here, this is 5. 5 is red and odd. All right. So there's a challenge here. Okay, you have lost that bet. Maybe we should just quickly compute the probability of getting a red or odd. Okay, so let's quickly try that. Maybe if you had placed that bet on red or odd, you would have gotten, of course, you would have won the bet. But probably you didn't place the bet because red or odd was probably a smaller, probability. Let us check so that we're not assuming. So we're going to calculate, and we're going to work out the probability of a red or odd. And then we also work out the probability of a red and odd. Of course, you know that the probability of a red and odd will be smaller than the probability of a red or odd. So just so that you don't, people will likely place probability bets on red or odd instead of red and odd, because red and odd gives you smaller odds. Okay, if you have a red and odd number, the odds are smaller. So interesting that the we are looking at odd numbers and we're checking the odds. So all right, probability of a red or odd probability of a red or odd. So the first thing we need to do is to we need to first compute the total number of red events. Okay, so what is the total number of, okay, let's write the formula first. We're still going to use this, a similar formula to this. Why? Because they are mutually they are not mutually exclusive. You can have an outcome that is a red and a odd. I'm guessing we might likely have the same probability here, so well, we should check. But the reason I'm guessing that is because we have the same number of red and the same number of black, and then we have the same number of odds as the same number of even. So computing this is more or less computing the probability of black or even. The only difference is that the outcome, of course, are different, but the number is going to be the same. So what's the probability of a red? It's simply 18 divided by 38, because there are 18, what's it called? There are 18 pockets that are red. Then what's the probability of an odd? 18 pockets are odd, so 18 over 38 is still this. And then what's the probability of a red intersect odd? That is a red and a odd. The probability is still this, because you are going to be having 10 elements in common. Are we? Maybe we might actually get something different. So let's check the roulette wheel again. So let's count all the outcomes, all the pockets that are both red and odd. Okay, both red and odd. So let's start from here. So we're just going to be looking at all the gray areas that are odd. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Voila. So we still have 10. Okay, 10 elements that are both red and odd. So that more or less still gives you this 10 over 38, which is this. So, you know, still pretty much everything we have here is what you're getting. All right. So you see, we didn't really get anything different. The odds were kind of equivalent. So, which is why you would just likely want to pick any of them, black or even, red or odd. It's like the odds are the same, so I just bet any of them. Okay, so when the ball now lands on a red that is odd, you know, you would place your hand on your head and say, hey, I should have picked red or odd though. But the odds are the same, so I don't want to use odds too much so as not to confuse odds and odd events. So the probabilities, so let me use probabilities instead of odds. So the probabilities are the same, so you really could not guess that one would favor you more. And you know the funny thing, even if one favors you more, like the probability of a black or red, which is as high as 0.9474, you know, something like this. As much as it favored you, you could still miss it, you know. And how can you miss it? You'll miss it if the ball spins into the green pocket. So even if your odds are high, that doesn't guarantee that you would always get it correctly. Okay, so this time around you were unlucky. The odds or the probabilities are the same. So you chose B or E, but it landed in R or E, and so you place your hand on your head. You lost that bet. All right. So what if something comes up in your favor? Okay, you are told, you know what? I'm going to give you a chance to place more informed bets. Okay. So instead of betting ahead, I'm going to make a spin. All right. And when I make that spin, the ball is going to enter a pocket, I will simply tell you where the ball landed, and then you're going to work out the probability based on what I tell you. So we have something additional here. Okay, I'm going to spin this. The ball will land in one of the pockets. Your what's it called? Um, your your job now is to take a guess. So if I tell you it landed on black, maybe guess whether it is even or odd, and then take a bet. All right, that's the goal. Now you can see something has changed here. We are not going to be placing bets based on information. I mean, just based on the information about that event. And the only information we have here is that we know the total number of outcomes for that event, and we know the total number of outcomes for the sample space. So you simply divide the number of outcomes for the event, like B or E, and then you divide it by the total number of outcomes in the sample space, which is 38. But now we are going to be having extra information of an event that has occurred. So a little bit of uncertainty has been taken away for us. We are told that, okay, the ball has spinned into a black pocket. So take a bet. All right, take a bet. So you are going to be calculating a probability that an event will occur, but you are going to be updating that probability with the information that has just been provided and information about an event that has occurred. So it is not the conventional unconditional probabilities you're going to be calculating now. Okay, you're going to be calculating probabilities that will be updated based on available information. All right. So the next bet you want to take now, you've been told the ball landed in a black. Okay, so maybe your next bet is even. What's the probability that the black pocket is also even? Okay, so you are thinking of this bet. Okay, what if I bet that black pocket is even? Of course, you don't know. It's insider information. The croupier looks at where the ball entered and sees that this is a black pocket. Okay, so you must take the next bet based on this information. All right, that's something has entered the black pocket. So is it even? Is it odd? Okay, we can even be thinking of other things like instead of even or odd, we can be thinking of specific numbers like is it 13, is it 10? But those probabilities are much smaller. Okay, the odds are so small. So instead of considering specific numbers, we consider colors like, we consider even or odd, okay, to increase our chances because there are so many even outcomes, there are so many odd outcomes. If you are looking at a specific number, there's just one specific outcome for that number. Okay, but if you're thinking of even or odd, there's so many outcomes, so the odds are higher, and that's what you're trying to do now. So our ball has entered a black pocket. What's your next bet? Are you going to take the even bet? Okay, so you are going to be updating the probability of an even based on the available information. So previously, the probability of an even event was 18 over 38, but it doesn't suffice anymore to do 18 over 38. Now that you already know that the ball has entered a black pocket, you now need to update that probability based on the information that the new sample space has changed to just all the number of outcomes for a black event. I don't know if I'm making sense. Anyone with me?
Okay. Whether they're even or odd.
Yes, thank you. So we are just considering the black pocket now. All right. So that probability is going to be updated. Now you want to calculate the probability and see how how that compares to your last bet based on the probability of a black or even. You want to check the number. Are the odds higher? Should I take the bet, or should I maybe consider, you know, um, that this next bet uh, um, is odd? Of course, if you're checking odd again, it's still going to be similar stuff because the number of even outcomes and odd outcomes are pretty much the same. Okay, at the intersection of black and red, you have 10 even outcomes and 10 odd outcomes, which is quite interesting. Now, yeah, so what do we do here? We need to um, make some slight do some slight changes to what we have in the sample space. Okay, what you're simply doing here is you are going to be considering a new sample space. Okay, so look at this intersection here. All right, you are going to be checking the probability that this black pocket is even. Okay, so it's slightly different from the probability of getting a black and even. A black and even, you can tell me the probability of a black and even. What part of this Venn diagram are you going to be looking at for black and even?
The intersection.
Yes, thank you. You'll be looking at the intersection. If you're checking black and even, you'll be looking at the intersection. Because if you think of the problem, it's like we know now that the pocket is black. So what's the probability that it's even? It looks like are we not trying to compute the probability that the event is black and even, that the outcome is black and even? In that case, we'll look at all the pockets that are both black and even, which means we're looking at the intersection. But that's not really what we're trying to do here. We're trying to compute the probability of getting an even. That's the first thing. So the focus is probability of an even. But given that the sample space is just this black, so take away all this diagram and everything outside black. Simply take away black prime. Okay, simply take away the what's it called, the complement of black. That's everything outside black. We're not going to be considering that. So in this sample space black, show me all the outcomes that are even. It is that those number of outcomes I now want to consider and divide by the total number in the sample space, which of course in this case has reduced to the number of elements in B, the number of possible outcomes you have for a black event. You see, so if you look at this diagram, here we have of course this is the entire sample space. For mutually exclusive events, we have 18, that is black, and assuming we separate black and even, it's 18. But by the time they cross at the intersection, okay, there are 10 elements in common. So we need to subtract the 10 elements here from this union. So the total number of elements in B and E, or B union E, that is B or E, the total number of elements is 18 plus 18, 56, minus 10, which gives you 26. So what you have left here, all right, out of 18 for B, what you have left here is 8. Then you have 10 at the intersection. So that 10 plus 8 gives you 18. I'm sorry, I should have probably further illustrated that on the diagram by writing the numbers. I should have further labeled. So you have 8 elements here. You have 10 elements at the intersection. So that's 10 plus 8 is still 18. Then you have 8 elements here. So that 8 plus this 10 is still 18 for even. So 8 plus 10 plus 8 gives you 26. All right. But now we want to look at the probability of getting even given that we now have a black. That is, given that black has occurred already, what's the probability that E might occur That's what we're trying to check here. So we simply now check the number of evens we have in the black space, and then that is 10. We now divide 10 by the total number of elements in black, which is 18. So 10 over 18. All right. So I can just quickly note that here, so that um, we let me use something else. So it's quite stressful when you have to write equations afresh. It's just better you copy and paste. You know, in my MSc thesis, this was what I was just doing for the next 104 pages, just writing bunch of equations. You can imagine having to write all these equations, and now you can't copy and paste because you'll be having different types of equations. Of course, you copy and paste once in a while, but you'll be having a lot of different equations. So it can be very, very stressful typesetting. But once you're used to it, you're faster than anyone else who just knows how to use words but doesn't know how to use the equations. All right, so the probability of event E, let me not say event E, so that we don't confuse E for event. E here is even. So the probability of even, given that B has occurred, that is black has occurred, what's the probability that we'll get an even, given that a black has already happened? So we're going to be updating our degree of belief in the event E by information available to us based on the event B that has occurred. So the uncertainty for us doesn't lie in B because B has happened, it's a certainty. The uncertainty for us lies in E, okay, in the event E, because E has not occurred. So this is where the uncertainty lies. Let me increase that. All right. So what are we doing here? Let's remove this. So I want to check the probability of E. I'm just going to write this as E given B for now. I'll write given in full. We'll introduce notation later so that we know the notation you use for words like this. Mathematically, we don't want to be saying English words. We just want to be saying letters and symbols. So we introduce that. So simply, it's going to be equal to, we need another fraction here. It's going to be equal to the number of elements in A intersect B. That is, we are looking for A and B. Okay, not A and B. Let me use E and B. Sorry. That is intersection of the event E, or the outcomes in E and outcomes in B. So E and B divided by the number of outcomes in what? What's the sample space now? Is it the entire S? Is this correct? Which means 10 over 38.
No. B.
So what are we going to have here?
B. Black.
Okay, B. So this is the probability of getting an E given B. Okay, so when you're looking at the entire sample space, it's like saying the probability of E given the entire sample space, but we don't really go further into saying given the entire sample space because we feel that's obvious. That kind of looks obvious. We only now start introducing given when the information that comes is now the information, new information that's available now updates or now makes us to update the sample space. So the sample space now reduces, okay, to a certain subset of the initial sample space. So the number of elements in E and B is 10. The number of elements in B is 18. So you see that this is going to change. If we compute this, it's going to give us, let's look at it, 10 divided by 18. So that's 0.555. It's a recurring decimal, so we just approximate to 0.5556 to the nearest 4 decimal places. So that's the probability of E, given that, event B has occurred. So we look at this bet. Now take a look at this. Okay, which is a better bet to take just based on that probability alone? If you look at what you're getting here, you are getting 0.556. So the probability that event E would occur, given that B has occurred, is 0.556. But previously we had that the probability of E or B is what? 0.684. This E or B or E, anyone. So it looks like it's smaller than the information that is available. By calculating the new probability of E, it looks like what we have now is smaller. So should we take the bet? Because it turns out that even with the insider information, our odds are a little lower than the probability of E or B. Okay, so it's actually less, but then it's still better than 50% odds. So it's still a good bet. We can still take this. Interestingly, even though this probability is lower than the probability of a B or E, the funny thing about probabilities is that we can get entirely different outcomes from what we place our bet on. Essentially, what you do, whether in business, in life generally, when you're dealing with outcomes in the future that have uncertainty, essentially what you're doing is placing bets. Okay, but people place bets without calculations, so sometimes they place bets wrongly. Okay, and they wonder why they keep losing. Then people place those bets with more informed calculations using probability laws, but they still make losses. So, but then you have a higher chance of getting your outcomes in line with your expectations. There's a higher chance for you to get um, your calculated outcomes than those that don't have knowledge of probability laws. There are people who play at casinos who are very good. Some of them are so good in the game, not necessarily because they know how to manipulate the laws of probability, but more or less like they know how to walk through, the whole scenario without having to do these calculations. Okay, so they are fast thinkers. So if you train your mind computationally, your mind can do these calculations without you consciously trying to do the calculations. So there are a lot of what's it called? This is an entire knowledge on its own. Um, Placing bets in casinos and all that. An entire body of knowledge for that. Even without going into probability, you can still make calculated guesses. Okay, so I was looking at I was looking at if I was reading a particular news today. Not news. I was on a website, and they were talking about uh, um, learning about how to gamble in casinos, and I just looked at the price tag for what you'll be registering for, and I just laughed. I said, look at all these things that we are doing here by just manipulating probability formulas. People would pay, $5,000 to $10,000 to learn those things, and what they're learning is still not, you know, it's like applied probability where they just give you the knowledge, you train your mind to think very fast about outcomes, but you don't need to, you might not, or you will not have to be using all these formulas. All right. And of course, there are softwares that people also use to get these things done. People cheat in casinos. People, there are a lot of things. I mean, if you watch movies, you just see a lot of interesting things about what happens in casinos and places where people bet. All right. So we've been looking at the roulette wheel, and it might seem like uh, this we are not trying to do a roulette wheel here, how does this apply in real life? First of all, the roulette wheel is real life because people use this to earn millions of money. So even if you lose, someone else has gained. Okay, so it's real life. But then all these things we are looking at apply interestingly to any situation or scenario in life where you have uncertain outcomes. All you just need to do is, check the possible events you can have in that scenario, and then work out the number of outcomes you can have, and then begin to manipulate these laws of probability. So the focus here is not really on the roulette wheel. We can apply this problem, we can apply, the intuition here to any other use case. The focus here is really on manipulating simple laws of probability to obtain results in real life. So whether you're betting on stocks, or whether you're trying to, you know, you're trying to place price tag on your products, you want to do pricing analytics, but you want to be calculative so that you don't overprice and you don't underprice, you know, whether you want to do any of these kinds of things, you want to make certain decisions under uncertainty that would impact your business, we introduce probability law. Now, some of these things we're looking at is the foundation. Of course, in business use cases, we need to go beyond just these simple formulas. We now need to start checking probability distributions, analyzing those distributions, checking various processes, and seeing the outcomes that arise from there. We can then do hypothesis testing. We'll now use some of these notions to check significance levels and check whether our hypothesis are right or wrong, or whether our hypothesis should be accepted or not, and so on and so forth. But we have to build it up. Okay, so just these simple laws alone can apply to so many use cases in life, in real life. So with this knowledge, we feel like, okay, data science is a long thing. Let me start gambling. Of course, you can just go ahead with this. You prepare to lose, of course, because you know that even if you have a 99% probability, as far as a 1% chance that there can be a loss, be prepared for that loss. So when you're making the bets and you're assigning how much you're going to make for those bets, then you have to be very calculative just to ensure that you don't lose too much. All right, coming back to data science, to probability. So yeah, we wanted to find how many pockets are even out of all the black ones. All right, and we've already computed that, and the figure we got was 0.5556. So the question we're asked, should you take this bet? All right, you can just say, okay, let me just go ahead, take the bet. Okay, so instead of the general bet of probability of B or E, of course, B or E is already out of the question. You cannot bet B or E anymore because obviously the pocket is black. Okay, so the question of whether B or E is out of it. Okay, the pocket is black, so you now need to now take other bets like, okay, I'm looking at an odd, okay, or maybe not odd. I'm looking at um something else, maybe a specific number. You can manipulate numbers, on that roulette wheel. Okay, the outcomes are so many. The outcomes in a sample space are so many, and by the time you begin to pull out various types of events, okay, the probability that I get a particular sequence of numbers, you may not consider colors. You may consider we have a black pocket. Okay, I mean, you may not consider whether it's even or odd. You may consider a sequence of numbers. All right, so you could check a sequence. You could check so many things, and then you begin to compute, which will give you higher odds. So that if you don't want to take, if you don't want to take the event E, given that you already have a black outcome, then you cannot look at other events. All right, but the what's it called still applies. Okay, the formula here still applies. So let us now look at what this really means in the language of probability. When you are trying to update the probability of a particular event given your new information about the occurrence of another event. All right. So what are we really dealing with here when we are talking about updating probabilities as new information arises? So this introduces the world of conditional probability, and this kind of the doorway to Bayesian statistics. So from here we can now look at Bayes theorem, and it's from here that we then begin to look at more interesting probabilistic reasoning approaches. So as I mentioned earlier, in the previous case, which is what we looked at in the last session, you're calculating the probabilities based on information that you have about the outcomes you're about to explore. Well, as new information arises about other events that have taken place, it can affect the probability of an event that you are looking at, that you're trying to explore. It can completely affect that event, or the probability of that event happening. All right. So in the previous case, we looked at how the information that event B has occurred affected the probability assigned. That's in the previous example we just looked at. We looked at how the information that event B has occurred affected the probability assigned to E. So previously, the probability of having an E alone is simply 18 over 38, which was 0.47 something. All right. But now that we know that B has occurred, you can see that the probability is higher. The probability is 0.5556. All right. The probability that E would occur, given that B has occurred, improved. Although that probability was still not as much as the probability of E or B, but it was definitely more than the probability of E. So you see that the probability of E has been updated. Previously, the probability of E, given this entire sample space, was 18 over 34, which is 0.47 something. But now, as we updated our knowledge about this event of B, the probability changed. So the probability of E now, given B, increased to 0.555. All right. So prior to the information coming, this P of E is called the unconditional probability, which means the probability is not conditioned on any other events. We are just looking at the probability based on what we know about the sample space, based on the possibilities that lie in that sample space. So the probability of E on its own in that sample space, as far as the sample space is concerned, is the original or unconditional probability. All right. But as information arises and we update our knowledge of the whole scenario, the updated probability of E, given that that event B has occurred, is called a conditional probability. Conditional because the outcome we're going to be having here is conditioned on this new occurrence, is conditioned on the information that B has occurred. So it is conditional. Okay, the probability we get is updated or it changes if event B has occurred. So this is the if probability. If a particular event arises and our information is updated, then E is going to change. So the outcome we get for E is conditioned on the occurrence of B. Now notice one thing. All right, this is very important. We still have uncertainty here, even though we are calculating the probability that B has, the probability of E based on information that E has occurred. We still have uncertainty here. If you notice, when we calculated the probability, we're getting 0.555, all right, but we still have 0.44, so we still have something to the uncertainty is still there, all right. So that you have the fact that B has occurred and you're trying to check the new probability doesn't mean there's no uncertainty anymore. All right. The only thing here is that now you have a little bit more certainty based on knowledge of this information. So the uncertainty here there's no uncertainty involving this event B. We know that it has occurred, but there's still uncertainty involving the event E. So this event still has uncertainty because we don't know whether it would occur. Even if we get a very interesting probability, an interestingly high probability, that doesn't guarantee that the event B would not occur. I mean, that doesn't guarantee that the event E would occur. All right. So B is certain, E is still uncertain. That's very important. So let's introduce some notation. Um, Now, we already talked about I already talked about unconditional probability, which is the original probability without access to extra information. But as new information arises, you're updating your degree of belief in that event based on the availability of information that B has occurred. So it is conditioned on that information, so it is conditional probability. We need notation now to describe that. So we simply use this notation. The conditional probability of the event E given event B, is denoted with this. So this vertical bar here is your given probability of E given B. In data science, you will see this notation a lot. Oh my God, if you are doing classification, this notation will haunt you. So, but once you know this here, it's very simple. You just remember. All right. So sometimes in machine learning, especially classification, we not only um, want to get a model that outputs a predicted class label, all right, that classifies the task for us. Sometimes we're interested in also knowing the probability that that class label is true or that that class label would happen. All right, so we want to know the threshold. What are the odds? All right, I want to know the power of this prediction. Okay, so instead of telling me that um, someone would default in their loan, tell me the probability, that they would default on the loan. So sometimes we introduce conditional probabilities, conditioning the likelihood of a particular event based on available information. All right. So based on this person's history, or based on this person's educational status, or based on what and what and what is the probability that this person will default? If you look at the entire sample space, we can just say P of E, or okay, P of default to be P of D. The entire sample space will just be P of D. So we are considering all the outcomes, all the possible outcomes. But let's say we now streamline the data and say, okay, let us only consider this person's educational background. Instead of considering all the variables in the data, let us consider this person's background. So what's the probability that there will be defaults given this background, educational background or educational status? Then we can look at other things like, okay, residential area and so on and so forth. All right, maybe the person's credit scores or credit history. Has this person taken a loan in the past and defaulted, or did he pay back his loan? So we just considered all those individual cases. So the use cases for conditional probability span much of data science. Okay, which is why probability is very important. The knowledge of probability is very important so that you don't get confused when you're dealing with some tricky notions in certain data science tasks, not just in machine learning, but also in decision science. Okay, so you may not be doing machine learning as a data scientist, you may be doing decision science where you're trying to make complicated decisions under uncertainty, and you're trying to run probabilistic simulations and trying to check various outcomes to know the optimal outcome and therefore make decisions along that line of outcome. So we call that decision making under uncertainty. Okay, so how do we arrive at P of E given B? That's probability that event E would occur given that black has occurred. All right, so we use this formula. This formula simply arises from the previous formula we've used, so don't get confused. Here we just considered number of elements in B and E divided by the number of elements in B. So we can simply say number of elements in B intersection E divided by the number of elements in B. But the exact formula for this conditional probability, instead of using number, we use probability, because we're trying to let you know that we still got each of these two we are still getting each of these probabilities by calculating them based on the sample space, the original sample space. What I mean by that is we're introducing P of E intersect B. So instead of just looking at the number of outcomes, we're looking at 10 over 18. Okay, E intersect B is 10, not 10 over 18, 10 over 38. All right, that's probability of E and B divided by the probability of a black, which is 18 over 38. All right, of course that boils down to 10 over 18. Let us do the math. Let's do the math. So instead of this, we are going to write we're going to do this. So probability of E given I can't find that symbol on my keyboard, so I'll just use symbols. All right, so we have this. So probability of E given B is probability of E intersect B divided by probability of B, which is probability of E intersect B is 10. Let me draw the fraction first. So probability of E intersect B is 10 divided by 38, right? And the probability of B in that entire sample space is 18 over 38. Obviously, by the time you do that, 38 and 38 cancel out, so it now boils down to this. So what that means is that I want the reason we use this formula instead of this formula is so that you will not confuse when we say n of b at the bottom. You already know that when you're calculating probability, whatever you have at the bottom is sample space. All right. So you may be interpreting this as the original sample space if we use this formula. All right. But if we use this formula of probability of this divided by probability of this, that should tell you that this is a probability, not a possibility. All right. Or at least before the event occurred, this was a probability. All right. So it means we originally had a sample space 38 and we are now trying to update it. So updating simply means you are cancelling out the 38 at the numerator by 38 at the denominator, leaving you with, you know, this new outcome 10 over 18. I don't know if that makes sense. Hope you guys are with me. So this is this. Does that make sense? I hope.
Yes, it does.
I hope the symbols are not getting too much and confusing, because sometimes mathematical notation can be really even for us mathematicians who are already so used to this. I mean, there's some research papers I'm reading, and it takes me a while to really catch up with notation, especially papers that assume that you already know the notation. And the funny thing about statistics and data science is you would come across a lot of materials that will use different notations. I mean, all we're looking at here, they're still good because the notation is kind of universal. But there's some areas where notation becomes totally different. You look at a vector and you think it's a matrix, and the author may not give you a glossary of notations where they tell you, okay, these are the notations we're using here, or the notation we are adopting here. So different materials have varying notation sometimes for certain topics, and sometimes if I'm looking at such materials, it takes me a while for me to catch up with the notation in order to understand the tricks going on or the manipulations going on in that material. So this is your conditional probability. We use this formula And more or less, it's like, we are still trying to do what we are doing here, but by doing this, we are improving. I mean, we are reinforcing the idea that the original sample space was 38, and now we are checking a sample space of 18 out of 38. All right, and then we are checking, this. So this 10 out of the 38, we're checking that. 18 out of 38, we're checking that. Of course, 38 cancels 38, and that gives us this. All right. So this is your formula for conditional probability. Now this equation leads us to the multiplication rule. Okay. So from here, sometimes you want to calculate not this. Sometimes you want to work your way to this. All right. But you have this information that have been given to you in the problem. So you need to just know how to manipulate the whole thing. Sometimes you need to calculate this numerator, probability of E intersect B, but you are given this and this, so you have to calculate this. So you can get the multiplication rule from here. So the conditional rule is division based, but you can now manipulate this to get the multiplication rule. All you just need to do is to multiply both sides by the probability of B, so that on this side, when you multiply by probability of B cancels this at the denominator. Then on this side, when you multiply by probability of B, it's simply a product. So by that, you can get or arrive at probability of E intersect B, which is simply equal to your probability of E given B multiplied by probability of B. Okay, so remember we had a formula for probability of E intersect B. E intersect B is probability of E and B. I don't know if you can remember the formula for E and B, but it's a very messy formula. Let me show you. I don't think we really drew out a formula per se, but we kind of used it in our calculations. So look at what we have here. We have probability of B or E, which you simply compute by adding the individual probabilities and subtracting the intersection. So which means the formula for this will simply be to make this the subject of the formula, a very fast trick. Since this is minus, just flip these two. Okay, interchange this guy at the left hand side with this guy at the right hand side, and you already have your formula for P of B intersect E. So that's a very fast trick. Whenever you see a minus here, okay, flip. No sign will change here, you just flip. Okay, but if you want to be more rigorous with your explanations, okay, if you want to know how you arrive at that, we add this guy to both sides. All right, so that we are going to have plus P of B intersect E here on the left hand side, and by the time we add it to this side also, it clears out because negative this plus this is 0, so it clears out. All right, so we have this plus this on the left hand side. Now we need to take this guy that way, so we subtract both sides by P of B or E, so that this guy lives here, leaving only this guy here. All right, and then we now have this one coming here. So it's still the same method I did. So instead of going through all that long process, when you see something like this and there's a minus here, and you want to make this guy the subject of the expression or the formula, simply just switch. All right, switch. Nothing else will change except that these elements would be interchanged. So your probability of B intersect E is simply probability of B plus probability of E minus probability of B or E. So from the notion of conditional probabilities now, when information is now available about the outcome B, okay, we now use this instead as a formula, which is quite shorter and probably easier to remember. The only thing is that I think the only thing that will be a problem here is knowing the order. Okay, So if we have E intercept B, then probability of E given B, it's whatever we have here will come first. That is the probability of interest or the event of interest. Whatever we have here would come second, which is the event that has happened already. All right. Then multiply by the probability of the event that has happened. You know, the event whose information was just provided to us. Okay. Of course, probability of E intercept B is still the same as probability of B intercept E. You know, but you just need to be very careful. You can actually write this as probability of B intercept B is still equal to probability of E given B times probability of B. Okay, so I think what really matters is getting it right at this right hand side. This left hand side, you can do B intercept E or E intercept B. It's the same thing. But on this right hand side, you have to be careful. If E comes before B, then the probability we're going to be talking about here is B. If B comes before E, what are we going to be talking about here? Yes? So I think
That's
that.
probability of E.
Yes, probability of E. So you have to be very careful. In this particular case, luckily for us, we'll be getting the same results when we compute this. Okay, so when we compute this, we'll be getting the same answers. All right. So let's try to compute this based on the information available here. All right, so compute the probability of E E and B, and probability of B and E based on this. Okay. Um, Maybe to experiment, I might change some values. Okay, or maybe let's work with what we have here. So let's put those formulas to a test. All right. What's probability of E and B from or using the multiplication rule? Using the multiplication rule. All right. So we just need this guy. So we're interested in this, right? So from here, we want to get probability of intersect B. Of course, you already know this probability, but let's assume we didn't know that. All right. So what are we going to be doing here? The probability of E given B is 0.556. All right, 0.5556. Then we're going to multiply that by the probability of B. And what's probability of B? Probability of B is 18. Okay, so we'll multiply this. Obviously, we're going to get, we're still going to get 0. What is 0 point? No. Let me just.
Sorry, probability of B18 was 0.4736.
Sorry, sorry. I was looking at 18/38. So 0. What? 0.4736.
4736.
Yeah, thank you very much. You are very attentive. Okay. So I'll multiply that. What does that give us? 0.26331 or 32. Actually, it's 0.263111. but because of approximations we've done here, that kind of affects the result. So let's see what we previously had for probability of A intersect B and whether we are truly we are truly on track. Well, I can remember that what we had was actually 0.2632. Just a second. Let me align this. Okay. So interestingly, when you're writing equations on PowerPoint, we can't do this alignment of this equal to sign. We can't align the equals. We can only do the alignments in Microsoft Word, which is very funny because more or less like they are the same tools that you're given. So what's the probability of B intersects E is this. So yeah, we're on track. Oh, my gen has gone off. Just a second, guys. Okay, so if you compute all those probabilities, if you compute that probability, you're still arriving at this probability of the formula probability that we had, which is probability of E and black. Of course, that probability doesn't change. Probability of E that is even and black. That probability doesn't change because if you look at this, it's just always the same, irrespective of whether we are now looking at just black and ignoring other portions of the sample space. It still remains this, this intersection. The intersection doesn't change. Then if we now look at, okay, probability of E or of B given E, that is, we're switching this now. Let's say you already know the even event and you want to get the conditional probability of B based on or given that even event. All right. If you carry out all the computations, you will get a different result for your probability of B given E, but your probability of B intersect E will still be the same with probability of E intersect B, and it will still be the same even if you didn't have the conditional probability. It will still be the same if you're working with just the unconditional probabilities. I hope that makes sense. So moving on, let us look at probability trees. Sometimes visualizing, we want to visualize probabilities we're talking about using Venn diagrams, which is where set theory, the knowledge from set theory becomes very relevant. We try to use Venn diagrams to kind of visualize what we're dealing with here to make it easy for us. Okay, but sometimes these probabilities might be very difficult to visualize with Venn diagrams, especially when they get more complicated. So we use what we call probability trees to, probability trees to visualize the probabilities that we have. All right, so you can have two branches. I've made some illustrations here. I got this diagram that made illustration, so thankfully I didn't have to draw that myself. All right, so what you can do instead is, let's start from the base. Okay, all the colors we have in the sample space, we have three colors: 18 black pockets, 18 red pockets, and 2 green pockets. So we simply create a branch. All right, or we simply create branches for them. Now, after creating these branches and specifying the probabilities of obtaining each of those individual events, all right, we then further branch by looking at, okay, this black event, how many odds do we have? We branch out. How many evens do we have? We branch out. So we actually have 10 even events and 8 odd events for black. We have 10 odd events for red and 8 odd events for red. If you remember when we're computing, let me take you back to this problem we had here, and we took the bet B or E, and maybe the ball landed in a red and even event. All right. I think I made a mistake in that computation, because what we have for red or odd, okay, it landed in red or odd, so the probabilities were the same, red or odd, because as it turns out, the number of odd red was equal, okay, to the number of even black. So black or even, all right, the probability of black or even turned out to be the same with the probability of red or odd. Well, let's say we're not looking at red or even. So assuming the ball eventually spun into a red pocket that was even, then we might have, we'll look at the probability of getting a red or even and compared to the probability of getting a black or odd. And I think, no, a black or even. Okay, so this is definitely going to be less. A red or even will be less, because instead we'll be doing R or E. So the probability of a red is this, the probability of an odd is smaller than this, and the probability of a red intersects, no, the probability of an even, not odd here. No, the probability of a red is this, the probability of an even is also this, but probability of a red intersect even will be smaller, because now we have lesser elements for odd. All right, not here. So let's come back to probability trees, and now we'll be looking at, all right, so we branch out. Now we check for green. Of course, they're just really the same, so 1/2, 0, 0, 0. All right, so the probabilities for each of these two pockets are the same given green. All right, so this probability and probability tree kind of helps us to visualize the possible outcomes in that sample space. So it might be useful where a Venn diagram will be too complicated to visualize what you have. It might be useful to use a probability tree. Okay, so but then there's something interesting about these probability trees. Okay, so in each of the cases, the second set of of, of branches simply show you the probability of outcomes given the outcome of the branch it's linked to. So this one is linked to the base branch, which is the entire sample space. So probability of black given the entire sample space, which is simply just the probability of black. It is the unconditional probability of black. This one is the probability of red given the entire sample space, so it is just unconditional. Okay, so even though we say given the entire sample space, it's like this is everything you're considering. So we don't really call it conditional probability, because you are dealing with the the omniscient here, if I should use that term. You are dealing with the complete space. All right, then the probability of green given this. Then when we come to this next branch, the probability you get here is probability of this given this. All right, so the probability of your odds given black is 8/18. It's no longer the probability of your odds, because the probability of odds is 8/38. All right, 18/38. The probability of your odd is simply the sum of the probability of this and probability of this, probability of all the odds. The probability of your even is simply probability of this and probability of this. But probability of odd given black is 8 over 18. The probability of even given black is 10 over 18. The same thing applies to all these scenarios here. So these next each next branch or each set of branch, okay, shows the probability of outcomes given the outcome of the branch it's linked to. And by the time you now get to this, this first branch, given the roots of the tree, because like a tree that has branches, and then at the very foundation is the root. So the root is the entire sample space. I hope that makes sense. So at the root, you have 38 possible outcomes. So this probability is simply the number of possible outcomes in that scenario divided by the outcomes here. But by the time we now get to this next set of branches, okay, the sample size now changes to the sample size of this. The sample size of the denominator changes. And by the time you add these two probabilities, they must make up 1. When you add these two, they must make up 1. Add these two, they must make up 1. All right. Add all this together, they must make up 1. So for each set of branches you're considering, all right, when you add the probabilities for the outcomes, okay, in each of the branches, they must make up 1. Now, it's not only possible to visualize probability trees, to visualize probabilities or conditional probabilities using probability trees. It's also possible to even calculate with them. Okay, so you can calculate, various other types of outcomes using probability trees. You can manipulate information using probability trees. You can manipulate various conditional probabilities using probability trees. Let's look at this particular case where you have a different number of branches, and there are 2 events here. Okay, 2 levels of events. You have A and A prime. Okay, A and A prime. Then you have B and B prime. All right, so A prime refers to every possibility that is not covered by A. Of course, you already know that when we use prime, it's simply the complement of an event. So A prime is simply everything outside A. Then B prime is every possibility outside B. All the possibilities that you will not find in B, possible outcomes in B that are not in B are in B prime. All right, so you can find various types of probabilities, like probabilities involving intersections, simply by multiplying the probabilities of the linked branches. Okay, so you can use probability trees to carry out computations. You can make certain computations or different computations, but remember that a conditional probability is simply the probability you compute given its relationship with the originating branch. All right, so when you're looking at the probability in this case here, at this level, this is a conditional probability conditioned on this. This probability is conditioned on this, and so on and so forth. So we can use this now, given our information about this. If we multiply this conditional probability by this original probability, it gives us the probability of A intersect B, which is simply the equation we saw earlier, right? We just multiply the adjoining branches together. Okay, so you can check the probability of A prime intersect B simply by calculating or multiplying the probability of A prime intersect B by probability of B. So you see, with a probability tree, you just create a tree by branching the various levels in the problem, and with that, you might not really have to stress so much before computing the probabilities. All you just need to know is, how do I find the probability of B? I simply get the number of possible outcomes for the event B, divide by the number of possible outcomes in the sample space, which is at the root here. All right, and then B prime, everything outside B, or everything that's not covered by B. Okay, I simply get that number, divide it by the total elements in the sample space. That gives me probability of B prime. The next level now, I will now do conditional probability. So what's the conditional probability of A given B? Okay, how do I compute that? I simply, you may be given the probability actually, but if you're not given the probability, you know obviously you have to work it out. All right, so you have to work it out simply by taking the number of elements here. All right, the number of elements you have now here at this level divided by the number of elements in the updated sample space, which is number of elements in B. That simply gives you. So with that, you can simply calculate the intersection. All right. So you use the this conditional probability formula in two ways. You can use it from here if what you need to calculate is conditional probability itself. But if you're trying to work your way to the intersection, you now use the multiplication rule. And the multiplication rule and the actual conditional probability formula are actually the same. They're equivalent. In fact, they're very equivalent. Okay, before I get there, so if you have any questions, let me quickly take your questions, but I'll be going through a set of, some questions that typically arise when we are looking at these various probabilities or conditional probabilities, because you have talked about so many things, and they can be quite tricky. Okay, they can be quite tricky uh, um, to bring them all together at once. It's like a lot to take in initially until you start getting used to it. So I'll just examine some of the questions that usually arise when we normally deal with conditional probabilities. We have looked at various things like various notations: the probability of B, the probability of A, the probability of A union B, the probability of A intersect B, probability of A given B, probability of B given A, all those things we've looked at. And then you'd have to now be careful interpreting these various types of probabilities in order not to mistake one for the other. So if you have any questions, let me take your questions before I look at the frequently asked questions, if I should call it that way. I don't know if time will permit us to go into Bayes theorem tonight, so I'll just record that. After the questions, I was looking at treating Bayes theorem, but it's already 10, so Bayes theorem might take us into 10:30. Of course, for Antile, that would be 11:30. They are 1 hour ahead of us. All right, so in the absence of questions, I'll just ask these questions or answer these questions. All right. So some of these questions arise when we deal with when we're looking at conditional probabilities and all the various notations. So one of the questions, or the first question is there really a difference between P of A given B and P of A and B? Okay, that's the probability of A given B and the probability of A and B. Because it's like we're considering the probability that A would occur given information about B. Okay, isn't that the same as probability of both A and B? For example, the probability of getting the event even, given the occurrence of black, isn't that the same as the probability of getting both black and even? Number one difference is that this particular probability is based on calculating we're trying to calculate the probability of A, okay, which means we do not know the outcome of A, but we already know the outcome of B. So our calculation of A is based on our knowledge, or is updated by our knowledge of B. But in this case, the two outcomes that make up the event, or the two set of actions that make up the event, are also, there's uncertainty related to them. A has not happened, B has not happened. So we want to check the events, the probability that the events A and B would happen, A and B will happen together. Neither of them has happened yet. So we're combining the two into one event and trying to check the probability of the occurrence of that event. So we'll look at all the possible outcomes in that space or in that subspace. But here that we have A given B, B has happened already. Okay, so our computation of A now is we're now trying to update the previous probability of A. We're trying to update that probability by computing the new probability based on the based on the new information about B that has been provided for us. That's essentially what we are doing here. I don't know if that makes sense. Hello, are you with me?
Yes, it is.
Okay, that's very important. So in this particular case, we cannot make assumptions that any of the two events has happened. All right. So you have to find the probability of both events happening without making any assumptions. You just simply check the possible number of outcomes and try to, you know, try to um, compute the whole thing given all the possible outcomes in that space. But this one has happened, and so that event, that occurrence, has provided it has provided an assumption for us. So relative to the occurrence of this, what will this outcome be? So we're not really trying to compute the outcome of A and B, like the outcome of A and the outcome B. We're actually trying to compute the outcome A, but conditioned on the updated sample space B. That's essentially what we're trying to do here. So second question, doesn't it mean that P of A is just the same as P of A given B? You know, could it be that P of A given B is just the same as P of A? Since we're looking at probability of A, all right, doesn't it mean it's the same thing with this? No, they're not the same. Okay, they're different probabilities. Because when you're calculating this one, P of A given B, you have to assume that the event B has happened because it's based on that information that B has happened. All right, but when you're working out A, you're not making any such assumption. The only thing you know is that you have a sample space and you have outcomes in that sample space, and so you have to compute the possibility of occurrence A, possibility of occurrence of A. Then another question is probability of B given A looks like probability of A given B. Are they the same? Now this one is quite tricky. All right, and it can be, yeah, it's quite tricky. But remember one thing here. All right, you look at this probability or this event B given A. You have to interpret which one of these two has occurred and which one are you trying to compute or to estimate. So for this one, which one has occurred? And for this one, which one has occurred? So let me take the responses. So in this event, B given A, which one has occurred and which one are we trying to estimate?
A has occurred. We are trying to estimate B.
Okay. How about for this event?
B has occurred. We are trying to estimate A.
Very good. So by that difference alone, clearly we have an answer. They're not the same. They're very different. So this is the probability of getting B. We're trying to compute the probability of a B, of getting the event B, given that A has already happened. Here we're trying to compute the probability of the event A, given that B has already occurred. So we're finding the probabilities of different events. So they're not the same. Now this one says if A and B are mutually exclusive, all right, what is probability of A given B? Probably should check this. okay, based on the formula that we have, let us check. Let us try to do. Let's try to work our way around. Sorry about that. We have done probability of E given B. What if these were mutually exclusive, like probability of E given R given B? I mean, before I do any computation here, I want you to just first think about it. We have two mutually exclusive events, R and B. All right. So what is the probability of R given B? Let me use this.
I think that's probability of B given R.
Yes, whether probability of B given R or are you saying the probability of R given B is also the probability of E given B given R?
No, it's different.
Okay. So I want the probability of R given B, probability of R given B. So the croupier tells you that the ball spin into black. So place your bets. You are not considering R. Should I bet R? I don't know. I want you to think about it, okay? R and B are mutually exclusive events. Now the croupier tells you place a bet. The ball landed in B in a black pocket, but place a bet. Okay, so you're not checking, okay, should I bet R given this information I just received? All right, so without the information, probability of R is just 18 over 38. Clearly, you already know that. But with this available information now, is it going to make sense for you to bet R, or what is the value you get when you bet on R based on the information that the ball landed in a black pocket?
I think that would be 0
It's 0. Why is it 0?
because they have nothing in common. Like they are mutually exclusive.
Okay. Yes, they're mutually exclusive. That's what we said earlier. But how does that now turn it to 0? Intuitively, if you think about the problem, it's 0. Okay, but mathematically, how does it really become 0? And change this to R.
You cannot compute.
Can you hear me?
Yes, we cannot compute a probability for R, given that the ball lands in B, because R is not contained in B.
R is not contained in B. Is that really very correct to say? Because yeah, clearly R is not contained in B. But that
Sorry,
would
Mr. Zion, please can you
that
go through the question again?
yes, I'll do that. Because if you say R
Somehow
is not
tricky.
contained in B, if that's the reason why you have 0, then it's like saying for this one, E is contained in B. Okay. We cannot really say
Yes,
E is contained in B. The only thing we can say is that um, when you just look at the subset B alone, we have some elements in E that are in B. But the event itself, the entire event itself, E, is not in B. Otherwise, you're simply saying E is a complete subset of B. And that is like not very, um, it's not very accurate. Okay, all our listeners, I should go over the question again. So what I'm trying to say is, um, you the ball spins into a black pocket. Okay, you are asked take a bet if uh, uh, um if you guess correctly, or you give the correct what's it called, then you win the bet. So to know your odds, you begin to calculate various conditional probabilities. Should I bet on the fact that the event is um, should I bet that it's an E? All right, it has already entered the black pocket already. Okay, but you are still asked to take a bet because you don't know exactly what other feature about that pocket A pocket can have so many features. It can be a specific number. It can be a black color. It can be a red color. It can be an even. It can be an odd. So you want to check so many things. Okay. So what if I say it's an E? What would be the result? Which means probability of E given B. What if I say it's a red? I already know it's a black. But what if I say it's a red? Which means probability of red given B. What would be the result? If I say it's a red, the croupier says that's entered the black. I say, okay, that's a red. But before I say that, I need to compute the probability. So what would be the probability of red given black? Does that make sense now? Does that make sense? Hello? Olawale, did you get the question? I can't hear anything from Olawale. So Marian, can you hear me? You were telling us
Yes,
it's
I can hear
zero.
you.
Okay, you were telling us it's zero. So you are correct. But I want to know either the intuition or the mathematical step at arriving at zero. Frances says she's lost in the class. That's because you missed the previous session. So much of what we are dealing with here is like a continuation of the previous session. We had calculated various probabilities earlier. Okay, so please, that first session is very important. Go over it again. It was like we were looking at very simple details. You know, in fact, everybody in the class practically knew everything we were doing because the whole steps were so easy to work with. But this class, we're taking a step further, so it's easier to catch up if you attended that class. So I would suggest before you go over this recording,
Okay.
make sure you start with that one. Sorry, Marian, are you saying something?
Yes, if you wanted to know the mathematical representation.
Either the intuition behind the zero or um, the mathematical progression to arriving at that zero. Because there's the intuition behind it,
Okay,
even if we
for
don't go into the equations.
probability of red intersection B, that's
Okay,
the
this.
it will be zero because there's no element of R of red contained in B.
Thank you.
There's no element of R contained in element of B. Of any-
Yes.
Then that will be zero over probability of B, which will turn out to zero.
Zero over what?
Over the probability of the black, which will
Okay.
be zero.
Okay. So that's it. R does not intersect with B. They are mutually exclusive. So the probability of that one already is zero. By the time you divide zero by any number you have here, is zero. Okay. But intuitively, if you look at the croupier tells you the ball lands in a black pocket. What is our red? Place a bet. Okay, and then you say, I think that's a red. It does not make sense because already you know that a black cannot be a red. So, and a red cannot be a black. So there's no outcome in the sample space where a black is a red. So that rules out red completely. So the moment, if initially you wanted to bet red, the moment she gives you this information that it entered a black, you're updating that knowledge and you already know that you can't get a red. All right. So initially the probability of a red, okay, just this alone is what? 18 over 38. All right. But by the time she tells you that we have a black here, you now update that probability as the knowledge is updated. Okay. You now look at it that the sample space is now black. There's no red in black. There's no outcome where a red is a black or where a black is a red. So you cannot have a black pocket that is a red, and where there's no outcome, it's zero. All right. So therefore, that event is an impossibility. It's not a rare event. It's an impossibility. It's zero. cannot happen. All right. So this one is like the long mathematical way of now arriving at the answer. Maybe not long. Probably this one is even shorter to explain than what I just explained. But in both ways, both explanations make sense. Sometimes there's some mathematical notions that you can actually interpret intuitively, right? But one thing is that the higher or the deeper you go in mathematics, the more necessary it is to suspend intuition, because there are some things that even if we try to make analogies, we must not make claims that the analogy is what we're trying to interpret. All right, we can work from an analogy to an interpretation, but we must never say that the analogy leads to the interpretation or the analogy is equivalent to the interpretation. Mathematical precision is usually unmatched by any other kind of explanation you can possibly have. All right, so some things are just strikingly mathematical. You can't explain them with the exact precision with which you explain them mathematically, and so we just stick to the mathematics, which is why sometimes mathematicians cannot explain to the rest of the world about some very deep research they are working on. All right, they can't just explain it. How could they? There's no way they would explain it without losing significant precision, and they're not comfortable with that because it means what they have explained is totally different from the phenomena they're trying to describe. Okay, so the only way they can explain it is using mathematical language, and the only people that can understand mathematical language at certain levels is mathematicians themselves. Even physicists will run away sometimes from some mathematical notions or some mathematical concepts because the precision there is heavy, and so we try not to make interpretations because the mathematicians would attack us. They would notice the slightest error you make, and they will just they'll give you counter proof to what you're saying. So we just avoid it totally. If we need to work on a problem, we collaborate with them. So intuition sometimes can explain some of these things, but there are times when intuition will fail. We just have to really speak in the language of mathematics. Thankfully, much of what we do in data science, we can describe them um, using intuition and analogies. We don't always have to use mathematical language, all right? But that's when we want to describe them. But when you want to understand them, we need to not go into all these details. Imagine if I was teaching you probability from that roulette wheel, and all I was just talking about was the roulette wheel. It will be so abstract, despite the fact that you're seeing a physical object. Sometimes we think abstract is these equations here, all right? But let's say I just did this. Let's say I just did this. I just gave you this roulette wheel. In fact, let me go back to the one here. Let's assume I've been talking for the last 2 hours just on this slide and telling you, okay, the probability of a black and the even is this, and it would be abstract. So now you're seeing a physical object, but the notion and interpretation is abstract. So people think abstract is formulas and equations and mathematical interpretations, but abstract is really relative. Sometimes the mathematical equations, as long as you can understand each notation and symbolic representation, they are much more descriptive than even the physical objects we're trying to describe. Because in fact, we're using these representations to unravel those physical notions that we're trying to understand. Okay, so this is just the power of mathematics, which in this case is still quite fundamental. So in fact, the probability for data science is very fundamental. Even when you get to more advanced probability, maybe probability distributions and probabilistic modeling, trust me, we have not even scratched the surface of probability theory in mathematics. All right, I think I'm going to stop here for tonight so that we just continue next week. I would continue this recording and finish with base theorem. I want you guys to pay attention to that because I will not be doing that in this class because of time. That should take another 30 minutes. So when you are going over the recording, try to pay attention to base theorem. But I think what I would do is I will just give a very simple explanation here. So basically what Bayes' theorem is doing is we have calculated conditional probabilities, like probability of B given A, but we now want to do the reverse. Okay, so given this available information, all right, let us reverse our calculations to get the reverse conditional probabilities. All right, so that becomes, or that gives you the foundation for Bayes' theorem. So I would talk further on that, and it turns out that Bayes' theorem is very much relevant to data science. Okay, so even if you're doing classification, you would see a lot of usage of Bayes' theorem, especially when you're trying to carry out probabilistic interpretations of your predictions. Then you want to use Bayes' theorem, or Bayes' rule, as it is called in data science. So the reason we call it Bayes' rule is because if we say Bayes' theorem, all right, it will force the person describing it or explaining it to give a proof. All right, so mathematically, you don't just throw around the word theorem. All right, so if you say theorem, give us a proof. But if we say rule, it's more science. It's more of general science to say rule. But if you say theorem, it's more of mathematical, which means for every theorem there must be a proof. If there's no proof, it's not a theorem. So give us the proof that tells us about this theorem. So in data science, we don't want to, except if you just like mathematics, we know that this is a theorem and it works. So we don't need to check, and it has been proven. We do not need to check whether it is true or not, because we know it is true. So we don't need to go over all those details. So instead, we just change the term. We say Bayes' rule. All right. So we'll be stopping here for now. I can take questions very quickly if you have questions. Otherwise, we'll stop here. Any questions? Any questions?
Any questions?
Well, from me, I don't understand anything.
Yeah, well, like I said, it's that you've not been. I mean, we're not in a previous class, so it takes some time to catch up with the notions. But I believe those who were in the previous classes would totally understand what we're doing here. Just trying to do this. All right. So as I was saying, once you go over the recording, trust me, you would understand what we're talking about. All right. So don't panic. We are
No problem, sir.
yeah good to go. All right. So that'll be all for tonight. Oh, I just saw this message now from Antile. Probability of red and black is 0 because of mutual exclusivity. So probability of red given black would be 0. Yeah, that's correct. That's very correct. All right. So I guess that's a good night. Me, I will just continue the recording here. Then we'll catch up with it. It's easier to walk through Bayes' theorem once you already have foundation of conditional probability. So the rest will not be so much to it will not be so much to understand. Okay, so Bayes' theorem will be easy to relate to. Yeah. So that's it. Let's stop this presentation. Okay, I've stopped the presentation already.
All right, sir. Good night.
All right, guys. Yes. Have a pleasant night.